All right, let's have a discussion, please. You can work quietly as we finish here. Hopefully you've had a good chance to take a look at this warm-up on that piece of paper, and we'll now say what the answers are. We can't really go over the drawings very well, unless just someone wants to produce them up here. Actually, I can just show you the answers. I have my key somewhere. Maybe do I? That's a good question. Let me see. Yeah.
Peter, I didn't say it. No, you know. Dude, Albert buzzed it.
All right, this is like a pretty sludgy version of it, but here. All right, this is not actually the answer key I'm looking for, but it is the same problem.
Wait,
this is not made by me. Disclaimer. Found this somewhere in a rubble pile.
I plugged this into my calculator. Oh my god. I didn't get the same answers.
I don't know. This is the same function, I think, isn't it? And everything. Are those not the answers you got? Okay, good. Units are dollars, just straight up dollars. By the way, does this curve even make sense for the situation? Why would the company charge more? I hope you understand. This is not like the curve. It's not like what do we actually interpret this as? This is the total cost for digging the whole mine. So the total cost. This is like the total cost of digging it. For digging just the 40th, like the rate of, this is weird because the cost function that was given is like a rate function, right? It's like dollars per, what is it, meter or something? So why would it make sense that this would go like uphill? Like explain that piece just real world wise to me. Like that actually does make sense, I think. You wanna?
The deeper it goes, the more expensive it is per meter.
Yeah, it's like please don't, like I'd much rather dig between 3 and 4 meters than 99 and 100 meters. Like suddenly that's a completely different problem. Like the first problem I can like maybe handle with shovels. The second problem I need like heavy machinery and pile drivers and like you're right. This is a big problem. So of course it's going to cost more per meter when we're down lower because we have to like bring in all sorts of new equipment and so that makes sense to me. And then this is the total cost we're calculating and this is. I guess there's not, the average isn't on there up here, but you did that, right? Did you average them? And you notice that it's not quite the same as this. We've said that a couple times, but it's a little different than like MRAM. Anything else you want to say about that one? I don't know. There's just more practice for us on this. Yeah.
I got 154,000
for which one? LRAM?
I ran this.
Well, you don't need to use the program. There's no need for the program.
No. I plugged in 0, 20, 40, 60, 80, 100.
Into the function?
Into the function. I got the Y. And then I added the Y, right?
So did you add,
multiplied by 20.
and you plugged, what did you plug in? 0, 20, 40, 60, and 80?
Yeah, into the equation.
You're only adding 5 things up?
Oh,
right?
Sorry. My equation was 0.6 like square instead of 0.06.
I did that too.
Yeah, okay.
Oh yeah.
All right, there's no shame. There's no shame. Okay. Let me say. So I think that's good for now. Again, emphasis on that. You saw. I can bring it back up if you like, but you saw the kind of work I'd be expecting of you. Either write out. If we're doing equal subintervals, then you can do whatever the delta x is, 0 to 20 or whatever times, and then in parentheses. If there's not equal subintervals, then you need to do each, length times width, or height times width for each one. But show me kind of the setup here. It's sufficient, like it's set up there, to just say like p of 0 plus p of 20 plus p of 40. That's fine too. Whatever, somehow to communicate that like you understand what you're going on, what's going on there. Okay. Okay. So we have 2 goals today to introduce to you. One small. The main goal is to talk about the trapezoidal rule, and we'll get you there and make sure you feel good about that. The second goal we'll start with today, and that's just to like to give you finally this notation you've been looking for. You've been using it, or you've been doing this all along, but we can actually like give. There's no sense in waiting to give this notation to you, so we'll give it to you right now. Here it is. The other thing, again, another piece of like language and technicality is that these are called, I don't know, have I slipped and even said it this way a couple times? These are also sometimes called Riemann sums. The things the way you're,
Use the math.
the guy that they're named for, right? But they're not, but those are always rectangular sums. So the ones we've been doing are all Riemann sums. It could be unequal intervals. Either way, those are called Riemann sums. And then we said that we have delta x. We haven't actually come out and said this, but I kind of prefer to wait on the formalization of this. But it is true that we can calculate, like if you wanted a formula for delta x, like there it is. But I prefer like to have you have a bunch of experiences around just like being like, oh, no one needs a formula for that. We're just like taking the interval and dividing it up. That formula will become more important to you though, as we move forward, I think. But just keep in mind that is in fact what you've been doing all along. And then we said yesterday too, just as a matter of review, we said we can finally like talk about this limit, and I think I showed you this picture. Right? This is just kind of review, capturing all this stuff. Just trying to give some formal language to this. Is there anything new that I've said so far? Riemann sums, that word. Delta x equals b minus a over n. I don't know if anyone has actually said that out loud yet, so there, it's been said. And then the last little piece of like kind of technical language is to actually introduce this integral symbol to you, right? And that looks like this. Right, so that thing we've been talking about, the limit as n goes to infinity, like rather than writing this every time, we'll be writing this. Okay? Because yeah, it makes you feel smart, but keep in mind that all it still is like adding up rectangles, okay? Like make no mistake. This is still adding up rectangles, though this encompasses, this is kind of like, just like in the limit form, we have like the secant becomes the tangent. Here we have like the sigma becomes the squiggly, right? So every time you think derivative, you're thinking limits, you're thinking instantaneous. Here, every time you see, instead of a summation, you're thinking here discrete. Here you're thinking kind of continuous, right? Which is cool, because this is kind of like pokey, this is kind of smooth. Okay, so, all right, yeah.
Can you go back for some more?
I will, yeah. So all that symbol means is the area under the curve from A to B, right? Provided f is positive, those things mean the same thing. Now we still have a lot of unpacking to do with that symbol. I promise I'll go back a slide. Okay, but why is dx a good name there for what's going on? Because it's supposed to just like kind of replace the notation here. Why is so many people who are excited about this? Go ahead.
Because delta x is the change in x, and then dx is like with respect to x.
Yeah, so we still have, at least in some sense here, we still do have like echoes of this original notation here. We do still have kind of the area of a rectangle, don't we? With height f of x and width infinitely thin dx. Right? And the fact that we can see that like kind of all alone is maybe an okay thing for you. We did start separating differentials in the last unit, so maybe that makes sense to talk about just a small change in x by itself. So again, there's a lot more to unpack there, and we call a and b the lower and upper limits of the integration. X happens to be the variable of integration, but keep in mind that that's actually kind of just a dummy variable. This, in the end, just comes out to be a number. If a and b are constants. Then we get like an area. You get a single number from that calculation. Whatever the function is called the integrand. So, in the warm-up it was whatever the function was. It might be a quadratic or something like that. That might be the integrand, whatever the function is. All right, and then so I just wanted to like get that, and now we're going to go back to trapezoidal approximation. Here, we were going to do lots of, I mean, approximation is is a huge business we have. We'll let this resource introduce to you the idea of trapezoidal approximation. It's very appropriate. We got a Star Wars movie coming out soon. I need to go back a slide for Josh. Is it okay if I do that? I'll come back. I can come back. Is this what you want to do? You're going to be working on this for the next few minutes? I'll give you, I don't know, 10 minutes to work on this. I think that'll be sufficient. And we'll summarize in a few minutes.
I'm good.
You good? Okay. So I'll come back, I'll come behind and summarize in exactly 10 minutes. We'll pause the video too. For the folks at home, I'm not recording. In this case though, by B1 and B2, go back, roll this back to the original. By B1 and B2, of course, we mean Y1 and Y2. And by H, remember we were oriented this way, H is actually delta X, isn't it? Keep that in mind. If you rotate this back and think about where we came from, that was the width, is actually the height now. So don't get confused there. So the area is just the sum of all those things. Look at how we have it. And if you want a quick way, if you want a little bit of a shortcut here, if they're equal widths, then you can use distribution again to help you. You can factor out some common things. Like it's just irresistible to maybe factor out the 1/2 and the delta x and multiply by those afterward, right? In fact, it's also we also notice that we get kind of some doubles in between. But notice, of course, that the first and last thing are not doubled. Again, not magic or voodoo. It's all just because of like where we came from here. It's just if this confuses you and you're like, I forget, do we not double? Like to the person who says that, like, wait, which ones do we double? Like, stop. You're not allowed to use the formula. Go back and just use the right. Just add up trapezoids. Like if you don't just forget that it's. This is not like a formula to use. It's just it makes it a little more efficient to do this calculation. That's all. That's all. To factor out but never lose, please, just like the rectangles, never lose sight of where you came from. It's just trapezoids, okay? Like in fact, that's a general principle. Like you're not allowed to use formula you don't understand. Okay? So taking that all in at once, all in that one slide, that's a pretty slide. There's lots going on there. That like captures what we're doing with the trapezoidal approximation method, doesn't it? So I have it in a box here, but whatever. It's the same thing as on the last slide. This does give us a better approximation of either the left or right. So let's maybe at least set this up. I know we're like running a little short on time, but TRAM4 on this integral right here. Let's actually, I know you can run it on the calculator, but neat. Let's do it by hand and actually show you how this works, right? So 1 to 2, what's our delta x? Yeah, isn't it 0.25? So, where are we going here? So what is TRAM4 going to be? And notice we're using this like new notation here too. This is good for us. Okay. Is equal to 1/2 times delta x, which we just decided was 1/4, or 0.25, times, yeah, we're going to use 1 squared plus 2 times 1.25 squared plus 2 times 1.5 squared. This is just like our function evaluated at 1 Do you understand where the 2 came from after our discussion? Plus 2 times 1.75 squared plus 2. Notice again, we've doubled the inside ones. Didn't double the last ones. That's what I meant. I need you to be able to write that and understand what we just wrote. Yeah.
How come we have 5 terms in there? Don't we have 4 trapezoids?
Yeah, we only have 4 trapezoids.
Oh, I see.
That's true. Yeah. Yeah, go back and think about that. Every single one of those segments is being used in the area calculations we're doing. Okay? Alright, I guess we won't get to that last example. Alright, someone can tell me what that comes out to be while I pass out your homework. It's this worksheet to answer your question, Nick.
He's like, that's the word I see. Dude, I want to be.
I think everybody got homework, right?
No, man, I'm sad.
Yes. Trapezoidal rule homework, it says at the top. Let's practice this new technique tonight. See you tomorrow. Please also finish this other worksheet if you didn't. Star Wars. You said it, Earl.